This is the third part of the second lecture, and we're going to talk about perceptual constancy. So perceptual constancy is another example of how your brain goes beyond just the simple stimulus that is presented to it. Perceptual constancy refers to the fact that we perceive the constant properties or features of objects in the world, even though the sensory information we receive about these attributes changes whenever our viewing circumstances change. An example of this that you can demonstrate to yourself is to hold your arm out at arm's length with the palm of your hand facing your face. Then move it farther and closer, so back and forth away from your face, so your hand comes close to your face, and then you move it far again, and then you bring it close, and then you move it far, and so on and so forth. You don't have to do it more than a few times. Did the size of your hand change? Was it bigger when it was closer to your face than when it was further away? Chances are not in any appreciable sense did it change size. Yet if you think about the image that's being cast on your retina, it's changing quite dramatically. When your hand is close to your eyes, it basically is taking up a huge section of your retina. But when you move it far away, well, relatively far, arm's length, it takes up much less space on your retina. So in a way, the image cast is smaller when it's far away and much larger when it's close together. Yet you don't perceive your hand as changing size. You don't perceive it as growing when it comes close to your face and shrinking when it goes away. This is an example of perceptual constancy, or more particularly, size constancy. So the first type of constancy is shape constancy, and this refers to the stability of shapes even when our viewing angles change. An example of this that you can demonstrate for yourself is a door opening and closing. If you look at a closed door head on, it obviously looks like a rectangle. Now, if you open this door and keep watching the door itself, the door doesn't actually become not a rectangle. You still perceive it as a rectangle, even though the image that is being cast by this door on your retina is continuing to change as you move it through the door's motion. The second type of constancy is size constancy, and this just refers to the stability of sizes of objects when our viewing angles or distances change. And the example I used of the hand moving back and forth from your face but not changing size is an example of this. The last one we will discuss is brightness constancy, and this refers to the stability of brightness or hues when the intensity of light changes. So an example of this would be if you were on a picnic on a much cooler day than today, and a tree was casting a shadow over the table you were using, and you had a red tablecloth across the table. You would not perceive the red under the shade as a different color than the red that is not under the shade, even though the degree of activation across your retina is different for both of those two places. So how does your brain do this? One of the primary ways is that your brain is very sensitive to the relationships between things that are presented on your retina itself, instead of just the absolute sizes and brightnesses of what is presented to the retina. Now, when your hand was moving back and forth, while the size of the image cast on the retina is changing, growing and shrinking, the ratios between the various aspects of your hand are no longer changing, whether you move it or they're not at all changing when you move it close or far away. The ratio of the length of your fingers to the width of your palm doesn't change no matter how close or far away you bring your hand from your eye. Now, a second way in which it maintains this constancy, though this is more for shape and size, is using cues of depth. So your brain is quite acutely aware of the depth or distance objects are from us, and it is able to use this along with the retinal projection size, so the image cast on the retina, to establish this form of constancy. And this can be something seen through proving it in optics if you want to look at the sort of physical dynamics of it. An example of this would be if your brain could multiply that an object is 10 feet away and it casts an image of 0.5 inches on my retina, which would be huge for inside your retina, but just for example. And then if the object is now only 5 feet away and it casts an image on the retina that's double the size, multiplying both sets of these will give you the same product. I'll get 5 by multiplying 10 and 0.5. I'll also get 5 from multiplying 5 with the 1 inch. And this is a way in which your brain is able to compensate for different viewing angles. And as surprising as this may be, your brain is able to do all sorts of math. without actually doing math as we do it. So another example of this is that you can hear sounds and effortlessly know where those sounds are coming from. And this actually takes some pretty interesting mathematical calculations to do if you wanted to do it on paper. Of course, your brain does it with neurons, and it processes it in a way that is not like the math that we do outside our brains. One of the best ways to see these types of constancies or processes happening is through the use of illusions. So here there are two monsters, one chasing the other maybe, or both just running down the hallway, and chances are is you see the monster in the back as being larger than the monster in the front. And the reason this is happening is actually the retinal image projection of both monsters is the same size. It has the same amount of space that is being occupied on the back of your retina. That being said, the cues of distance are quite different. We see the monster in the back as being larger because it's farther away and on the retina the same size as the one in the front. And this is what gives rise to the illusion. And if you don't believe me, check this out. Here are two lines to show how tall each are, and then we will put them next to each other. And yes, one is a little bit lower than the other one, but they're functionally speaking exactly the same size. Even though, no matter how much we have knowledge of this, we cannot not see the illusion. Another one is shape-based illusions, and so here you could think about which table is longer, and chances are you will almost always select the one on the left because it looks much longer than the more square, rectangularly shaped one on the right. And we ultimately see this illusion because of how we're perceiving not only depth, but these objects as three-dimensional as opposed to the two-dimensional objects they actually are. So here's just again a way of illustrating that, drawn the two sides, and if I put these two together, they're basically the same length. And this is a pretty hard one to wrap your mind around, so if you don't believe it, you can try tracing one and putting it on top of the other. Sorry, these are a little finicky, but trying to make cutouts on a screenshot with a mouse is not the cleanest thing in the world. But as you can see, that is the cutout shapes of both tabletops. And even though you can see the two parallelograms on the bottom as being identical basically, no matter how you look at those two tables, they will look like they have different shapes. Finally, a little bit about brightness illusions. So just to give you forewarning, the values I will give you for the three squares that matter are RGB values, and this just refers to how much red, green, and blue is in them, and this is how you encode basically colors into pixels on a computer screen. You can also use something like a PowerPoint or a Photoshop tool to find out what the exact numbers are for any given spot. Now, square A and square B don't look the same color at all. B is way lighter than A, but the actual measurement of those values that is going into our eyes, or at least created by the computer screen you're probably looking at this on, they're the same. I mean, they're off by one, but that's probably just my own little measurement error and how I was moving the little cursor around. Even stranger still is square C, which looks exactly like square A, is actually an entirely different color than square A, which is pretty wild. And this ultimately has to do with the fact that our brain is compensating or adjusting those colors to take into account that a shadow is falling on them from this little cylindrical tower that is present. One last note, the reason no matter how much you know about these illusions, you cannot unsee or not see those illusions is due to the fact that all of this processing is happening in an unconscious manner. Not that we're passed out when we do it, but rather that we have no conscious access to these types of processes and adjustments. It is always on and always going on in the background.